Alright, so in today's video, we're going to start off by saying that this is going to be a course on differential equations. And what will be covered in this course are going to be the following: ordinary differential equations. And what we will look at is how to define, or simply the order of the differential equation. We are also going to talk about if it is homogeneous or not. And we're going to look at linear and non-linear ordinary differential equations. We're also going to look at how to solve differential equations. So these are the main four objectives during this course. So we will go ahead and understand how to find the order of a differential equation, whether it's homogeneous or not, whether it's linear or non-linear, and we're going to solve some differential equations using various methods. So, by the end of this course, you'll be able to model real systems and translate laws into mathematical equations. And you're also going to be able to solve the solvable differential equations that can be solved. You're going to master analytical techniques for the most important ordinary differential equation types. And we're also going to learn how to approximate some solutions where exact solutions don't exist. And we're also going to interpret solutions, basically extracting the physical meaning from mathematical results. So, what will be needed for this course? A solid understanding of calculus, meaning that you will have to understand derivatives, you have to understand integration. You would also have to understand techniques used for integration. For example, U sub, integration by parts, and partial fractions, and partial. And if those are rusty, then you need to review them so you could understand and succeed in this ordinary differential equations course. So to say the least, you need to have a solid foundation of calculus. So we're going to go ahead and look at the simplest case for differential equations, the separable differential equation. So, for example, let's look at this equation. What is this equation telling us? Well, this differential equation tells us a quantity grows at a rate proportional to its size, meaning that the quantity y grows at a rate proportional, which is a value k, to its size. So what this means is that pretty much our quantity y is going to grow at whatever k is. And how do we find the solution to find said quantity? Well, what we can do here is simply separate everything with a y on one side and everything with an x on the right side. So here we could divide by y. So we will get 1 over y dy over dx, and that is equal to k. Now we're going to multiply by dx to end up with 1 over y dy. So we have 1 over y dy, and that is equal to k times dx. And here what we can do now is simply integrate both sides. What this will give is simply, if we've taken integral calculus, we will know that the integral of 1 over y is simply ln of y. And the right side will simply be equal to kx plus c. And we're adding the constant because if we are given a initial condition, for example, let's say we have y of 0 is equal to something, then we would plug in x equals 0 and y is equal to whatever, and then solve for c. But here we have to solve for y now. To do so, we will exponentiate both sides. So the ln and the e are going to cancel out. So we have y is equal to e to the kx plus c. We could simplify it just a bit more. So if we look at the right side, we have y is equal to e to the kx times e to the c. Where this, simply we could rewrite this as c because e to the c is simply a constant as well. So it is going to be c. So the solution is going to be y is equal to c times e to the kx. And that is going to be the solution to this separable differential equation. So we see that we have a quantity that is related to exponential growth. So in this case, this one equation models some of the following: population growth, pop growth, when k is greater than 0, and we could say decay for k is less than 0. We can also relate this to compound interest and cooling temperatures. So that's what we're going to understand and link with differential equations. Because one simple differential equation describes countless of examples and models that we could use. And we're also going to be talking about classification of differential equations, and we are going to understand what an order is. So for example, I'm going to just show a few examples so that you know what is going to be covered within the next lessons. So to find the order of a differential equation, what we have to do is simply understand that the order is the highest derivative present. The degree is the power to which the high derivative is raised. So for example, if you have y double prime plus xy is equal to 0, what would be the highest order derivative? Well, we have a second derivative. So we would say that the differential equation above has order 2. What about this one? Y prime plus 2y is equal to e to the x. We said the highest derivative is y prime. So this has order 1 because we have a first derivative present. But is this, what degree is this? Is this a first degree, second degree, or third degree? Well, since here we have a linear differential equation, this is simply going to be a first degree. What about the first one? What would be its degree? Well, since there is no power of a differential, then we are simply going to say that the degree is also 1. So both of these are first degree. But let's go look at a bit more tricky one. What about y triple prime squared plus xy double prime is equal to x to the 7? What would you say the order for this is? So here we have a order 3 derivative because the third derivative is the highest derivative that is seen. So the order is 3. But what about its degree? Is it a 7th degree or a 2nd degree? Well, let's look at the definition again. The degree is the power to which that highest derivative is raised. So our highest derivative term, which is a third derivative, it is simply squared. So this is going to be 2nd degree. So we see that identifying the order and its degree is fairly straightforward. Because here we have our third derivative squared. So the highest derivative is order 3, and it is raised to a power of 2. So it is 2nd degree. So the next thing we're going to talk about is linearity. And this is crucial. A differential equation is linear. So let's say if a ODE is linear, then we have to have the dependent variable y and its derivatives appear to the first power. So what this means is that a differential equation is linear, then it must look like this. Y prime plus xy is equal to 0. But if it has a power 2, 3, 4, then it is nonlinear. For example, if we have y prime squared plus xy is equal to 0, this is non-linear. But y double prime plus xy is equal to 0 is linear. So there's a difference. And the second statement is that there is no product of y and its derivative. So for example, let's say we have y prime plus y is equal to 0. This is linear, but if we have something like y times y prime plus 7x is equal to 0, then this is a nonlinear differential equation. So we see that there's a huge difference. While we could solve this differential equation that is linear fairly easy, it might be a bit more difficult to solve nonlinear differential equations. And a ordinary differential equation is linear if there is no transcendental functions. For example, let's say sine or log or an exponential of y or its derivatives or its derivatives. So what this means is that, again, we're going to use the same example. Y prime plus y is equal to 0 is linear. But what this means is that pretty much we cannot have, for example, y prime plus sine of y is equal to 0 as a linear differential equation, because at this point it is non-linear. The same thing with y prime plus e to the y is equal to 0. This is non-linear. As well as y prime plus ln of y is equal to 0. These are all non-linear. And this also includes for y prime. You don't need to just have a y for it to be non-linear. This also counts for something like cosine of y prime plus xy squared is equal to square root of y. This is non-linear because we have a transcendental function of y prime. And we also have a y squared and square root of y. So this is non-linear. So we see that none of these four right here are linear. So we're going to do a small test to check if a differential equation is linear. So we're going to test for linearity. So let's look at y del prime plus p of x, y prime plus q of x, y is equal to some function g of x. Would you say this differential equation is linear? Yes, it is, because we have y del prime raised to the power of 1. Y prime is raised to the power of 1, and y is raised to the power of 1. And everything except y prime is multiplied by a function of x. There is no extra y terms. So this is linear. This is a second order, degree 1 differential equation. What about y del prime plus y squared is equal to 0? Would you say this is linear or non-linear? Well, it is non-linear because of the y squared term. So we see that there's a degree 2 for y, meaning that this is no longer a linear differential equation. If this was gone and it was just 1, then it would be linear, but since it is raised to the power of 2, then it is nonlinear due to the quadratic term. What about y times y prime is equal to 1? Would you say this is linear or nonlinear? Well, here we have a product of y and y prime. So we see that this is non-linear because of the product. And finally, we are going to look at y prime plus sine of y is equal to e to the x. Would you say this is linear or non-linear? Well, because of the fact that we have a transcendental function of y, this is non-linear because of sine of y. So this is nonlinear. Why do we even care if a differential equation is linear or nonlinear? Well, the thing is, linear ODEs have a complete theory. So they have a complete theory. We can always find solutions because of the fact that there are multiple ways of solving differential equations that are linear. But nonlinear differential equations often require numerical methods or clever tricks to find said solutions. For example, we have y times y prime plus 7x is equal to 0. This nonlinear differential equation would be hard to solve, but this nonlinear differential equation does have a solution. If you were to go ahead and try to solve for this, you would see that there is a solution. So we're going to look at first order differential equations and the two main types that we will look at. So first order differential equations that we're going to look at is simply the first type, so type 1. And these are separable differential equations, usually taking the form of dy over dx is equal to g of x times h of y. And to solve this, we would simply multiply and separate. So we could just separate and integrate. So here we could simply divide by h of y and multiply by dx, which will give 1 over h of y dy is equal to g of x dx. And here we could finally integrate, and we'd have to integrate said terms to get the solution for y. And the second type is type 2. First order ODEs, which are linear. So we have y prime plus p of x y is equal to q of x. And the method we usually use to solve this is simply called the integrating factor. And we will get into the integrating factor method once we touch the topic of a first order linear differential equation. So these are the main types of differential equations that we will look at starting this course and how to solve these types. And we're also going to talk about the theory of high order differential equations. So high order ODEs. So now that we're reaching the heart of the theory, consider the general nth order linear differential equation. So we have an of x times y to the nth derivative plus an minus 1 of x y to the n minus 1th derivative up until a1 of x y prime plus a0 of x y is equal to some function g of x. So this is the general high order ordinary differential equation. And this exact differential equation is what we call a non-homogeneous. Because of the fact that g of x is not equal to 0. But if g of x is equal to 0, then we have a homogeneous ODE. So we're going to talk about the theory now. So let's just go ahead and clear this up really quick. So the key theorem we will talk about is called the existence and uniqueness theorem. So the existence and uniqueness theorem states that if the coefficients ai of x and g of x are continuous on an interval I, and the leading coefficient or leading function an of x does not equal 0 on I, then for any initial conditions at a point in I, a unique solution exists. So this is a key fact and theorem that we have to understand because this tells us why linear ordinary differential equations are so well behaved. And this is a very big theorem that we're going to get into later. We're also going to move on to homogeneous solutions, or simply a homogeneous case. So we consider a second order homogeneous linear differential equation, a2 of x y double prime plus a1 of x y prime plus a0 of x y is equal to 0. Then we have a superposition principle. So this superposition principle pretty much suggests that a general solution might be a linear combination of two independent solutions. But when are y1 and y2 truly independent? We're also going to get into that as we progress in the course. And finally, so now we're going to talk about the Wronskian and linear independence. This is pretty much a theoretical cornerstone of differential equations. And the Wronskian is simply y1 comma y2, and that is equal to a matrix y1, y2, and y1 prime and y2 prime. And if we find the determinant, then we're simply going to find that the Wronskian is simply y1, y2 prime minus y1 prime, y2. We're going to also look at a theorem, which is a fundamental criterion for differential equations. We see that y1 and y2 are linearly independent solutions of a homogeneous linear ordinary differential equation on an interval I if and only if the Wronskian of the two solutions is not equal to 0 for all x and I. And in the event that if there is a Wronskian that is equal to 0, then there pretty much is linear dependence. Because y1 and 2 are pretty much the same function, just multiplied by a linear constant. But if we see that the Wronskian of the two solutions, y1, y2, does not equal to 0, then pretty much at any point the solutions are not proportional everywhere. So the main consequence of this is that if we find any two linearly independent solutions to a second order homogeneous linear ODE, we found the solution, which is simply y is equal to c1 y1 plus c2 y2. But if y1 and y2 are simply linearly dependent to each other, then we are simply going to get y is equal to c y1. Since y1 and y2 are going to be the same, they're simply just going to be joined together because they are linearly dependent on one another. So yeah, so just a quick summary of what we're going to simply be learning. We're going to be learning how to solve differential equations. So let's just say summary. So the summary of what we're going to be covering this course is simply first order ODEs. We are also going to be covering high order as well. And we're going to be also looking at nonlinear ODEs. We're going to be talking about finding the order, degree, and solving. We're also going to be talking about the solutions of pretty much first order and high order differential equations and the techniques to solve. So we're simply going to be learning mainly these top 5. We might dive into other concepts that might not be mentioned here, but of course, those are going to be within a differential equations course. So, thank you for watching, and I'll see you in the first lesson.